Okay, we are in lesson 10.2, looking at series and determining whether they are convergent or divergent. So the previous lesson, you were to review the definitions of series versus sequences to remind yourself that sequence was just a pattern of numbers, and series is actually adding up, summing up the patterns. So series is a summation, and sequence is just list of numbers. All right. So in what we're going to do from this point forward in this chapter, all our series are going to approach infinity, because if we actually end the series at a certain number, it is going to add up to a sum. So it will converge no matter what. So that's why it says here, finite series will always, oops, sorry, that's bad color. Finite series will always add up to a number. So that way we don't need to worry about those. It's the infinite series that we're going to look at, right? And at this point, we're looking at whether or not a series is convergent. That means it's going to add up to a number, or it's divergent, which means it approaches infinity. Now, if it is a series, divergent means it will approach infinity because it's going to add up to a number it's going to add up to it's going to approach infinity where the sum is unbounded, right? But if it is a sequence that you're looking at, then divergent really means that it's just not convergent. So because it's not convergent, therefore it is divergent. It may not necessarily head to infinity. It just means that it doesn't converge to a single number or a sequence. Okay. All right. So there's this one definition you need to know before we start with today's ideas, is this idea of a partial sum. So this infinite series sum, is adding up all the numbers all the way to infinity, right? And that's pretty huge. Now, it's maybe a little bit too big to tackle. So then we do these things called partial sum. Instead of adding up all the numbers from 1 to infinity, or n equals 1 to infinity, we add up the first number, we add up the first two numbers, we add up the first three numbers, we add up the first four numbers. We add them up until we see if we can see a nice pattern. Because sometimes this is a very good way to check if it does add up to a good number. If it does create a pattern that we can recognize, and we can generalize that pattern, we can actually look at the sequence of this partial sum. We can look at the series of, we can look at the sequence of this partial sum, see if it converges. If it does converge, then the series itself converges, right? So here is a pattern number, a sub n equals 1 over n times n plus 1. This is the series, right? So that means that I have a list of numbers with this pattern. This is a sequence. I have a list of numbers with this pattern. Series means if I add them up, does this diverge or does this converge? Does it go into one number or does it go out into infinity, right? So this is a bigger pattern for us to see, and we'll take a look. All right, so first steps is to actually list the first couple of terms to see what we get. So a sub 1 here, we plug in 1 and do it 1 over 1 times 2, so it's 1/2, right? A sub 2 is 1 over 2 times 3, so 1/6. A sub 3 is 1 over 3 times 4 is 1/12. A sub 4 is 1 over 20. As you can see, this fraction is getting smaller and smaller. Is it fast enough? We don't know. But the pattern is hard for us to figure out whether or not it diverges or converges. So what is a little bit easier to do then, okay, we're going to take the sum, the partial sum, right? So we'll take the partial sum, we'll take one number, add them up. From this sequence, if I take the first number and add it up, it's going to be 1/2. Right? Add up the first two numbers. Sub 2 means add up the first two numbers. You get 1/2 plus 1/6, which will get us 4/6, which is really reducing to 2/3. Okay. S sub 3 is 1/2 plus 1/6 plus 1/12. Again, essentially adding 1/12 to the 2/3. And if you reduce your final answer, you get 3/4. Now, if you already see the pattern, you can stop here. Sometimes I need one more, so sometimes I do S sub 4. But if you don't need to, you can actually generalize at this point and see that, hey, the partial sum, this pattern actually gives me n over n plus 1. Very nice, right? So then now, because this pattern, you're able to generalize this pattern. So let's see what it does, right? We can look at the limit as this sequence approaches infinity. Will it converge to a number? So you take a look at the limit as n approaches infinity of this partial sum sequence, n over n plus 1, right? Plug it in, you can see that this is basically, this is a rational function, right? You can just take the higher power over the higher power, or if you are so inclined, you can do L'Hopital's, right? So if you do L'Hopital's, you get infinity over infinity. Okay, that means I get limit as n approaches infinity, 1 over 1. Limit is 1. Oh, so it does converge to 1. So this sequence of the partial sum converges to 1. So the sequence of S sub n converges to 1. Therefore, the series of A sub n also converge to 1. Okay? All right. So you have to support your answer a lot in this chapter. You have to support it with what you are doing here, with what is happening in this problem, right? You have to tell me, why is it converging? How do you know it's converging? How do you know it's diverging? You can't just say, oh, series converge and diverge, because it's 50-50 chance that you get one of them right. So you have to be able to support your answer, okay? Now, of course, there are lots of them that don't converge and don't give you a good answer. So let's see what the next one does, all right? So next one in our example is this, oh, sorry, by the way, let's go back to this. There's a name for this particular series here. It's called telescoping series. So we will refer to this later on in other chapters and later sections. So yes, just kind of remember that there's a name for this particular one, okay? All right. The next example here says it's -1 to the n minus 1. So again, for me personally, I do my terms first. I list 4 of them out, see if I can see something, right? So I plug in 1, I get -1 to 0 power, that's 1. If I plug in 2, I get -1 to the 1 power, so -1. A sub 3 is 1 again. A sub 4 is -1. Because of the n minus 1, the power just goes back. The even odd power makes our number go back and forth between 1 and -1. Now, you can already see that this number is just going to go jump from 1, -1, 1, -1, 1, -1. It's not going to converge. But we can use the partial sum to kind of further prove that and show us that it doesn't converge, right? So if I add one number, I get 1. If I add 2 numbers up, I get 0, because 1 plus -1 is 0. And I add another number, you get a 1 again. And I add another number, you get 0. So you can see it's not coming together. Therefore, this is terrible. Therefore, this diverges. And because this diverges, the sum diverges. The series diverges, okay? All right, here's another one. You have this thing called a harmonic sum, so harmonic series. So some of these have really beautiful names, right? What is a harmonic series? It's really a 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6 plus 1/7 plus 1/8 plus 1/9 plus 1/16 plus da 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 da. All right, so of course it's going to go on and on forever. There's a reason why I'm listing all these out. I know you can see the pattern here, but I'm going to show you why this one will diverge, right? So for me personally, I see this, I'm like, oh, how can this diverge? This is a number that's going down. The fraction is getting smaller and smaller. Maybe they do converge down to a nice number that it can add up to. So the idea is to kind of break this up. Here you have 1 plus 1/2, right? So it's already 1.5. So it's 1.5. Then you take these 2 numbers. You have 1/4 and a number that's bigger than 1/4. So if you add them together, you get a sum that's bigger than 2/4, which is bigger than 1/2, right? Oops, terrible writing. I apologize. All right, bigger than 1/2. Okay. Next, you're chopping them in powers of 2, so it's a lot easier to understand. Okay, here I have 4 fractions. These 3 are bigger than 1/8. So 3 things bigger than 1/8. So 1/8, bigger than 1/8, bigger than 1/8, bigger than 1/8, plus 1/8. So you're going to get bigger than 4/8. So you're going to get bigger than 1/2 again. And if you continue this pattern idea, you get bigger than 1/2. Every power of 2 separation here, you get bigger than 1/2. So you see how you're adding up these numbers. You have 1.5 and you add more than 1/2, so that the number is growing bigger. Add up more than 1/2, then growing bigger, bigger. So the sum is getting bigger and bigger and bigger. It's not converging down to a smaller number. This series is actually diverging. All right. And of course, later we will have other things that can actually further prove that this does diverge. Okay. All right, quick reminder, you had geometric series in Algebra 2 Honors or in Trig. A reminder, I'm not sure where you have seen this before, but this is a reminder that you have a pattern here that's multiplying by a ratio. What am I talking about? So a very simple pattern is something like this. You have 1, 1/2, 1/4, 1/8, 1/16, 1/32, so on and so forth, right? Each number is going up by 1/2, so your ratio, your common ratio is 1/2. Now, sometimes it's not going down, sometimes it's going bigger. So you can have 1, 3, 9, 27, 81. So my ratio is 3, right? So just keep in mind, if the ratio is smaller than 1, whether it's positive or negative, doesn't matter. If your ratio is smaller than 1, you actually have a really nice sum here. It's just the first term divided by 1 minus the ratio. If your ratio is bigger than 1, then it diverges, grows bigger and bigger and bigger. It never comes close. It doesn't close up into a good finite number. Okay? All right, here's another thing. This is called the nth term test. So we can check and see if something diverges. The nth term test is not super powerful. It is just something useful that if you can show that it diverges, your job is done. But if the limit, like it says here, so, okay, you take the limit of the sequence, not the series, but the sequence. So you take each term, right, and see if the term as a function is approaching 0. So if it does approach 0, that doesn't really tell us anything definitive. It actually just says you need further investigation. So you got to use other tests that we're going to develop in this chapter to test out whether it converges or diverges. If the limit approaches a number that's not 0, then the series diverges and our job is done. So it's actually kind of nice 50% of the time, right? Okay, so let's see. We're going to look at all these summations. We're going to look at all these series and see if we can have a nice conclusion here. All right, so you're going to treat the term, so limit as n approaches infinity of n over 2, n plus 1. Again, you can look at this as a higher power rule for fractions here. But for quotients, yeah, for rational functions. But or you can take L'Hopital's rule, up to you. It's really don't worry about it. But it doesn't matter which one you choose, right? So if you work on that, you see that the limit approaches 1/2. Well, because this is not equal to 0, this sequence will diverge. Diverge. All right, and your job is done. Okay. All right, how about the next one? Limit as n approaches infinity of 1 over root n. That would give me 1 over infinity, which is equal to 0. Because the limit does equal to 0, I need further investigation. And we'll get these investigations later on in the chapter, so don't worry about it, okay? Next one, you have limit as n approaches infinity of 1 over n squared. Same thing as 1 over infinity, which is 0. Again, this is another case where you need further investigation. The last one, limit as n approaches infinity of e to the n over n. Well, again, this one does need L'Hopital's rule. We're going to plug it in. We get infinity over infinity, okay? L'Hopital says then we can take the derivative of the top, which is still e to the n. The bottom becomes 1, so it's e to the infinity, which is infinity. Well, infinity is not 0, therefore the sequence diverges. The series diverges. Okay? All right. This theorem 8.19 is kind of interesting. It says if the sum of a sub n and the sum of b sub n are series such that a sub j equals b sub j plus c, so you're adding more to your sequence for every j that's bigger than k, then both series converge or both diverge. So it's a little wordy here. What this is saying is, all right, let's say you have a nice series of 1 over 2 to the n, right? So 1 over 2 to the n. So generally we start at n equals 1 and go to infinity. So your pattern really starts with 1 over 2, 1 over 4, plus 1 over 4, plus 1 over 8, plus 1 over 16, plus, and so on, right? Now, we know this is a geometric series because each number is going up by 1/2, and the ratio is less than 1, so of course it's a geometric series. We know then this will converge. So what does this formula say? What is the theorem trying to say? The theorem says, hey, what if you don't stop here? What if you take a different n starting point? So let's say I have more to my series here, right? I started here instead of at 1/2, I start at 4 here. Is this new series going to converge? Yes, because it is a part of a series that we know already converges, that whether we add the same pattern number to the front or we add the same number pattern to the back here and go 128, 256, 512, and so on. Whether we add to the front or add to the back, these series will also converge. So basically what this is saying is you can add or delete to the series. It will still be converging or diverging. Okay, so there's a homework problem that really talks about this, so make sure you refer to this theorem again. Okay. All right, theorem 8.2 I think is a little bit easier to understand. Basically, it's saying that, hey, if these two series are convergent and they converge to a number respectively, so this converges to A, this converges to number B. So you can actually add your you can add your convergences up. You can add your series up. If you add the series of A sub n to B sub n, then they will converge to a sum of A plus B. Same thing if you subtract the series here, then you will have the convergence of A minus B. You can also multiply it by a constant, a scalar. So if you pull it outside, same thing, it's going to be C times the number you're trying to approach, right? So your convergence number. So it's actually kind of nice. Okay, so we're going to use that to help us answer this question. Here you have this big series here. So it's a big, big formula, but we can break it apart. So for me, I'm going to break it apart. And by the way, at this point, a lot of our summations won't have these n equals 1 and infinity, because you can actually assume that all our series are going to start at n equals 1. It may start somewhere else, but it's going to go to infinity. So a lot of them are going to be blank. If it is blank, you can assume naturally that it is n equals 1 and it goes up to infinity up top. Okay. All right. So now we are going to check and see what this will do for us in terms of splitting up the summations, right? So you have 7 times n, 7 over 7, n times n plus 1, right? And then the sum of 2 over 3 to n minus 1. Well, this is if you take that 7 out, that's a scalar, that is a multiplication, it's a coefficient, right? Take that 7 out, you will see this is our telescoping series from above, our examples from above, right? And we know this converges to 1. So this part of our series is going to converge to 7 times 1, which is 7. Okay, now let's take a look at this other summation on the other side. So whenever I see something to a power like this, I usually think, oh, maybe this is geometric. So I have to check, right? So for me, I'm just going to take a really quick check here and see if I can see the pattern, see if I recognize the pattern for a geometric series. So if I plug in 1, I get 2 over 3 to the 0, which is 1. So that's 2. If I plug in 2, I get 2 over 3 to the 1, so 2/3. Plug in 2, I get 2. Plug in 3, I get 2 over 9. So you can see, and if you need more numbers to see the pattern, you're more than welcome to do more numbers. But here I can see that, oh, this is indeed a geometric series. My ratio is 1/3. Oh, so that means then this series will actually converge to a sum of A sub 1. So A sub 1 over 1 minus my ratio of 1/3. So that will give me 2 over 2/3, which mathematically gives me 3. So now a combination of these two series will converge to a total of 10. Okay, kind of nice. All right, last 2 quick ideas is to remind you, hey, if a series is convergent and the other series divergent and you add them up together, it's divergent. But be aware, if it's a subtraction here, that's not necessarily true. So if it's subtraction there, you might need to work in L'Hopital's a little bit more, because think about it, it may be infinity minus infinity, and we know that that doesn't always necessarily equal 0, right? So check on that. Secondly, if a series is convergent, then the limit of the sequence is equal to 0. But remember, it's not true for the converse. If the limit equals 0, it doesn't mean it's convergent. But if it is convergent, it means the limit is 0, right? So if I say the limit, if I'm looking at a sum of 1 over n, we know this is divergent. Oops. Before that, we're going to take the limit as n approaches infinity of 1 over n. That actually gives me 0, right? So limit is 0, but we know from above this is a divergent series, so this is not convergent. We are going to look at this one, and we'll talk more about this one in the next lesson. But this one, yes, the limit is 0, and this one is convergent. Okay, so this one, with more tests, we will see that it is convergent. So again, reminding you of this idea, this theorem that, hey, if it is equal to 0, it does not necessarily mean, right, that it is convergent. But if it is convergent, this limit will for sure equal 0. Okay, all right, that's it for today.